Perfect. Okay. Earth science time. Today we are talking about. We're talking about not making that noise. We're talking about surface. I'm not sure this is going to show up very good. Processes.
No, it doesn't show up at all.
It doesn't show up at all. A little better now? I'll change to black. I'll do dark blue. Let's do it. Okay. Surface processes. Surface processes. Those what? That what?
What? Those processes
Yes.
that occur on the surface.
Those processes that occur on the surface. Those. Remember, a process is in science a verb, a thing that is happening. It doesn't have to be in the way that we think of verbs as in present tense, like it's happening now. It can be a continuous thing. It usually is a continuous thing. And the location of that verb, the location of these processes, the location of the events that are occurring on Earth's surface is the surface, not at depth. So we're specifically talking about the things that happen at the interface between the geosphere and the atmosphere. Geosphere and the atmosphere. Are those all the spheres that are going to be involved, do you think? No, but the definition kind of the surface is where the Earth itself as a physical object, the geosphere, interfaces with the atmosphere. The place where land is here and on top of it is atmosphere. Under, rock. Over, air. So that's what we're talking about when we mean at the surface. What other spheres probably are going to be interacting with this? The biosphere. Featuring biosphere and the hydrosphere. Those are going to be the main ones. So there are different kinds of surface processes, and today we're going to be talking primarily about erosional and depositional processes. Or we'll call them media. So we're talking about the erosional media. And we have talked about several of these before. The topic of the last lesson was about erosional media and how it interacts with the sedimentary rocks. But we're going into more depth. This will be the third time that we talk about the kinds of erosional media. And we're going to be specifically talking about the, I want to say the word artifacts, but that's not really quite right. The physical objects that exist because of them. And the reverse of that when when we see these physical objects, we can tell what kind of erosional or depositional media caused them. Okay, so let's again, for the third time, list our media of surface processes. We have called them before erosional media, but of course every erosion ends in a deposition, just like every life ends in a death. Yeah, death is kind of the finality of the process of an individual life. Does it go on after that? That's not what this class is about. But in the same way, erosional processes always end in deposition. So they go hand in hand. It's not like we have one erosional process and then a separate depositional process. This is just the finality of this. Ooh, brown. I thought I picked pink, but I guess brown it is. So there's a deposition at the end of an erosion. So these processes are, if not exactly the same, they're just different names for the same thing. You can at least think of them as linked. They are hand in hand. What are they? What are the different erosional media, or they're different erosional? No. Okay, so water. Let's have subpoints below water. We're talking only about water ones now. River, which we call fluvial. Lake, which we call lacustrine. Ocean, which we call marine. Remember from your last test, rill and gully. What else? What other water ones are there, if any? What other water ones are there, if any?
No, that's not water.
Rain kind of goes along with rill and gully. If it's causing erosion, it's either a rill, or if that rill is permanent, it's a gully. Okay, what else? Yeah, we could say hydrothermal. Like geysers, etc. Okay, besides water, then, what other kinds of erosional media are there besides water? Oh, wait, we missed a big one. That was also your belt work.
Glacial.
Yeah, glacial. Good. Okay. Wind, and that we call aeolian. And then gravity, which we call mass movement. And we made this comment before. This is, again, the third time we made it. Even though this one is specifically gravity, all of the water ones are caused by gravity too. I mean, that's the energy source. And speaking of energy, in all of these, greater energy means what for the erosion and deposition? Greater energy equals what?
Greater
Bigger what?
force.
Bigger on
In any of these, the higher the energy is, the larger the what it can move. Yeah, the bigger sediment. So that's the fundamental principle of erosional media, is that the more energy that erosional system has, the larger the sediment can be moved. So we use the specific kinds. The point of all of this is that when we see a feature, a geological feature out in the wild, we can use what we know about the features, what kind of erosion it caused it, and what we know about the energy. We can identify, based on the size of the sediment, how much energy that process had. So when we go out in the wild and we see, ooh, a neat looking cliff or something, we can say, well, this cliff was caused by wind erosion because blah, 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 and it was this much energy of wind erosion because the size of the sediment. Okay, so that's what we do. That's why we learn this, is so that we can identify how features that are on Earth's surface formed. And we use the knowledge of the processes that are happening today happen throughout Earth's history to tell us about that. Okay, so here's our list. Tell me when you're done with the list, because we're going to go through it. We're going to talk about individual features.
What was under gravity?
Mass movement. We call that mass movement.
I have no questions.
Yes.
What's the other word that's with hydro?
Geysers. I put geysers there. Hydrothermal is geysers. Okay, so let's start with, does anyone have a pick? Which one would you like to start with?
Water.
Water. Okay, which kind of water?
Let's go river.
Let's go with river.
Yeah.
Okay, so let's go to river. We're just going to go down this list. I'm going to check them off as we go. So in river erosion, I shouldn't check it off until we're done. Idiot. Mr. Kime, you stupid moron. Don't check it off till you're done. So when we're talking about river erosion, so when we're fluvial, rivers can flow either fast or slow, based on what?
Gravity. Energy.
Okay, so most of the time we consider Earth's gravity to be constant. There are differences. There are differences in Earth's gravity, but generally we consider gravity not to be a variable. So it's not like there's more gravity here, and so this river is going to flow faster. So what is the kind of, you're right, the gravity is giving it its energy, but say it again.
Elevation.
Elevation, not even a word. It's not the elevation itself, it's the elevation relief. It's the slope. So the speed is based on the slope. Fast mountain stream,
Right.
slow meandering river. However, generally, slow meandering rivers are usually wider in, I don't know, in cross-sectional area. So these are usually narrow and fast, and these are usually wide, slow, and we use the word meandering. If we look at this one from the top, ooh, that's nice. This is a bird's eye view now, a map view. This one's cross-sectional, which is basically worthless, but this one's a map view. You should know that river erosion, fluvial erosion, especially in this case of a meander, it's not like the highway, right? If this were the highway, your dad is driving along and he would choose to turn right here, and then he would choose to turn around again, right? Water molecules don't do that. That's an important feature of this, is the water molecules are not driving. They're going in basically a straight line. And so anywhere where there's a place like this, that will be actively eroded, and we call that a cut bank. The water is moving faster, it crashes into that, and so eventually the river gets cut away, or the river bank, that is the land on the sides of the river, the bank, gets cut away. And here, the sediment is not moving as fast, and so it gets deposited. And so this builds up over time. And so over time, the river kind of shifts in this way. You can see, you might have, I don't know, maybe you're not on the same part of TikTok as I am, but you might have seen like time-lapse land satellite videos of the way that a river changes its course. And it does that because water molecules are stupid. They're not driving along the river. They're going in straight lines and crashing into edges called the cut bank and leaving behind the inside edges, which are called a point bar. And you should write both of those down. They are on the test. They used to be vocab words. They might still be. I can't remember what's in your lesson now. I'm going to erase the word map here. So the point bar is the not edge really, you wouldn't say, the bank of a river that is being deposited, and the cut bank is the bank of the river that is being eroded. And that causes a meander. That's why rivers curve, is because what starts out, you can see this curve gets curvier and curvier. What starts out as a relatively straight river over time takes on a snake-like meander, especially in the wide and slow areas. You see this when you tube on the White River, if you've ever done that. This doesn't happen very fast, but you can see the places, you get stuck in the places. If you're on this river, you do have a brain, most of you, but if you aren't paddling away from it, you get stuck here on the cut bank. Because you just, because the water goes in a straight line, and it leaves you behind. The water then reflects off and goes over here, but you get stuck there. The point bar is the depositional side, the side where the sediment is being deposited. So the meanders get more meandery, and eventually, some little bit of water, maybe over a long period of time, depending on how deep the river is, will get through here, and then it's all over. There's a shortcut, so this part gets completely cut off. This becomes an oxbow lake. So if you look at, especially this happens in the American Southeast, but anywhere where there's a flat plain with a lot of rivers, there will be excuse me, a meandering river going over the plain, but it'll be surrounded on either side by these lakes called oxbow lakes, which is like the remains of where a river meander used to be. When it gets cut off, you see now the water has a path of less resistance, and so it goes through this straight line instead, and this lake is cut off. And some of these can be very large and recreational-sized lakes. Yes?
I think it's cool looking at the Missouri,
yeah.
Almost like, not Arkansas, where like Tennessee is, all that whole part of the U.S. All those borders are, crazy curvy.
Because of the rivers, yeah.
But they're not there anymore.
That is interesting. I never considered that, but yeah, where the borders were put down, someone at some point said, this border is the river. And then later they're like, well, guess what? The river moved, so now is Tennessee bigger? No, the answer is we go by where the border was at that time that it was set down, and now there's not even a river there. Really interesting.
The original borders were like this, and now the river goes like this.
Yeah, because of this exact process. Really good. So what size sediment do you think this can probably carry? Small. Small sand at the largest, maybe, depending on the river, but sand at the largest. If you've ever been over the Missouri or the Mississippi River, these kind of wide, slow, meandering rivers, you will know that they look murky. They look brown, usually, because they're carrying quite a lot of silt and clay-sized sediments, and that sediment is wrapped up in the river. And that brings me to another thing. Let me finish that thought first. What size sediment do you think this fast, narrow mountain stream here? Large. Possibly boulders, depending on where it is and how the sediment has been, but pebbles can be overturned. Let me erase that, and I'm going to talk to you about this other thing. Within a river, and this is kind of true for all the erosional processes, but we don't always call them the same thing, but sediment can be moved in the following ways. Sediment movement. So for a given speed of river, the largest sediment that can be moved will be rolled. Let me spell the word rolled correctly. Rolling sediment. So sediment that's rolled along in the river. The next largest will be saltated, or that has the same root as sauté, which is French for jump. The sediment will be picked up I'm going to do little diagrams. Rolled, sediment will be picked up and then set down. So picked up and then it'll go for a while and then it'll sit down. It can be suspended, which is where it's kind of, like it's up within the confines of the river, carried along by the river. Or the smallest sediments, the atomic size sediments, are dissolved. And of course that only applies to minerals that can be dissolved, but they're just, I don't know what these diagrams are supposed to indicate, but you know what rolling is. So maybe for a fairly fast-moving river, pebbles could be rolled. Sand is saltated, that is picked up and dropped. Silt could be suspended, and maybe the clay size, it would have to be dissolvable in water, but the clay size sediment might be dissolved. Does that kind of make sense? So the larger the sediment is, the less movement can occur. This also applies to aeolian erosion.
So after a certain point, those sediments kind of dissolve into the water?
Not dissolve. Some of them can, depending on what they're made of. But after a certain point in time, they are either deposited, maybe they'll be moved later on, but they're either deposited or the river slows down and then they're deposited. But the end point of erosion is always deposition. In dissolved, they will crystallize out. In these other ones, they just stop and they just stay where they were. And maybe if the river goes away from that area, which does happen, the river no longer flows over that area, it solidifies into rock, and that's where we get a lot of the sedimentary rocks. And that's how we can tell what sedimentary, where they came from, as we look at the rock that is left behind. Kind of like fossils of a river. Did you write down these ways that things can move? Okay. This is true for all of these water ones. I'm going to erase this, but let's talk about this idea of a watershed. The definition, in America we call it a watershed. In your book it calls it a drainage basin, which is kind of a more scientific name. In Britain, and I assume in the other Commonwealth states, it's called a catchment, like an area where the water is caught, where it is catched. But it's an area of land where water falling will eventually get to that body of water. So every body of water, river, lake, ocean, or even a rill technically, has a watershed, has an area of land around it where if water falls there, that water will end up in the body of water. What's the nearest body of water? We're in a lot of different watersheds because they overlap, but what's the nearest body of water you can think of? The White River, yeah. So this is the White River watershed. If I take Kimber's Visco Girl Stanley mug outside and dump it, bloop, or I hope there's water in here, Kimber, or when the snow melts, the snow will eventually, that which doesn't evaporate, will run off into the White River. The White River is a tributary of what other river, do you know? No, well, eventually, but first the Niobrara. The White River flows into the Niobrara, and therefore the whole watershed of the White River is also in the Niobrara River's watershed. What does the Niobrara River flow into? The Missouri, and therefore the whole watershed of the Niobrara is within the Missouri River's watershed. What does the Missouri River flow into? The Mississippi. And so the whole Missouri River watershed is within the Mississippi River watershed. So they overlap. So are we in the Mississippi watershed? Yes. Are we in the White River watershed? Yes. I've drawn this diagram here of the Boreal Sea, but that's not what I want to show you. I want to actually erase that because I want to show you what I just told you, but I want to show you on the map. And I don't know this is going to pick up on the video, so sorry, Gunnar and Kesslin. And also, I don't care.
And Kendall.
And Kindle, yes. So here, you guys sit down here for a second. So here we are, let's say, boop, here's the White River. And so maybe the White River watershed is this little area right here. And maybe the Niobrara River watershed is a little bit bigger. And now the Missouri watershed is quite a lot bigger. So it's this area of land here. All of the water, I'm making these up, but I bet they're true. And then the Mississippi watershed is all of this. So we're within the Niobrara, and we're within the White River, and we're in the Missouri River watershed, but we're also in the Mississippi River watershed because they distribute into each other. Does that kind of make sense? Does a watershed make sense?
I do have a question.
Yes.
Does west of the continental divide? Does that go to the Columbia and Colorado?
Great. So that they would each have their own. The Columbia and Colorado would each have their own watershed. But you point out something great, which I almost missed, which is the word for the land that separates them. So this is the Great Divide, something like that, where on the east of that, everything will go into the Mississippi River. On the west of that, Colorado, Columbia, there's some other minor ones, but not the Mississippi River. But every watershed is bounded by divides, by areas of land higher. Good job. A divide is the word we use for the separation between watersheds or drainage basins, whichever you prefer.
What's the word after eventually?
Get. Yeah, crazy that someone would write the word get and they would choose to draw it in this way, but that's what I've done, so thank you. I'm going to say river. Check. Lake?
Check.
Sure. Because a lake, it's a place where water comes to and sits there, and the size of the sediment is deposited. Lakes are usually depositional media. The ocean is just bigger. Check. There are some things we think about with the ocean, and we'll talk more about these later on in the year if there's time. Tides, well, that changes, and currents. Tides and currents cause a change in sediment. But sediment moved by the ocean is usually very, 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 very small. Even though the ocean waves can get very large, the actual motion of the ocean is not usually strong enough to carry large sediments, and the sediment is far enough underwater that the currents in the ocean are not actually moving sediment at all. It's just water, except for the salt that is dissolved. That sediment is moved around. Rills and gullies, small little rivers. Geysers we're not going to talk about. No one cares. But we do want to talk about glaciers. So let's have a little side note on glaciers over here. We really killed a lot of that list at once, though. Glacier. So let me start this by saying that something I missed about rivers is that rivers, and you should put this back in your rivers notes, but rivers form V-shaped valleys. Basically, as a river cuts down, I'm going to put that over here. As a river, we look at the land from the side. A river cuts through, there's a little low point where the river is. As the river cuts down into it, the sides kind of cave in, and they end up forming this V-shaped valley. So even very, very, very deep river valleys like the Grand Canyon are fundamentally V-shaped. The V can be narrower or wider depending on the composition or how stuck together the sediment on the sides is. So like the Grand Canyon, where it's cutting through a lot of really compacted sediments, the sides are like this, but they're still roughly V-shaped. Whereas the Mississippi River, where it's cutting through soft sediment and only barely, since it's not a very strong erosional medium, might be very, 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 very wide. But they're fundamentally V-shaped because when it cuts through them, the sides cave in. And that forms a V-shaped valley. Glaciers, though, on the other hand, form a U-shaped valley. And these, you really, really notice these in the wild. Like you see a valley, like I know that's a U-shaped valley. Like it just looks like the sides are kind of curved in like that. So places like, there are no glacial features around here because the last time there were glaciers in this area, the entire world was under glaciers. It was like 500 million years ago. Yep, there are. So you don't have to go very far to find glacial features, but there aren't any here. But if you've ever been to like Yosemite National Park, or you say Eastern South Dakota, or especially places like, you haven't been there or I'd be jealous, but like the Alps, there are a lot of glacial features there. And the Alps brings me to another point, which is that there are two kinds of glaciers. There are continental glaciers that kind of cover enormous swaths of very flat land, and there are alpine glaciers, which are smaller in the sense that they are in a smaller area of land, but the glaciers are a lot of times deeper, and these form in mountains. So like the Alps, that's why it's called an alpine glacier, but also the Himalayas have alpine glaciers. So continental glaciers, there are some on the map. This, you can think of this is all a continental glacier. Greenland is covered in continental glaciers. But the Alps here have glaciers too. You can kind of even tell on this satellite map, there's a little white flecks that are alpine glaciers. There are also some down in the Andes Mountains. And then you can see them in the Himalayas here, those alpine glaciers. So those form by virtue I'm not going to write this down, but I think an elegant way to describe it is these form by virtue of latitude, that is how far away from the equator they are, and the alpine glaciers form by virtue of altitude, how far from Earth's core they are, up. So glaciers form a U-shaped valley, and they also, when they push sediment, push mixed sediment. You remember from your last test, I told a lot of you what this was because you asked, but do you remember what we call it in sedimentology when the sediments all mix together?
Yes.
Poorly what? Sorted. They push mixed sediment, which we call poorly sorted, into moraines. And a moraine is like, if you think of a glacier as like a big old icy bulldozer, the thing that's getting scooped in front of the glacier is called a moraine. And that's just a pile of all jumbled up sediment. And so if we see in eastern South Dakota, for instance, or Finland, a hill that is made of a pile of poorly sorted sediments, what do we think deposited that hill? A glacier. Similarly, they also form what are called kettle lakes.
And South Dakota has a lot of those.
Yeah, and the Minnesota, the land of 1,000 lakes,
Yeah.
that's all kettle lakes. Finland, Canada, those are all kettle lakes. They're lakes that are dug out by a glacier. So I mean, the glacier doesn't like scoop up a spot, but somewhere where there's sediment being plowed in front of it, maybe a little bit catches, and then the glacier pulls through that, and it gets a big old hole, which we call a kettle lake. When that fills with water, it's called a kettle lake. Trying to think if I missed anything. Eskers and drumlins are erosional depositional features of glaciers too. The drumlins are little hills that form where almost the opposite of a kettle lake, like where little piles of sediment are deposited as a glacier melts or retreats. And then eskers are snake-shaped hills that are carved out by a glacier too. So you can you look those up because they are in your book. Let's talk about wind sediment real quick. How much time do we have left? Does anyone know? I don't know what that means. How long do we have left? Okay. Okay, let's talk about wind. I'm going to put wind in brown.
Oh, you're right.
Aeolian erosion. So the wind, oh, sorry, let's check off glacier. That was a real quick rundown of glacier, but I liked it. Wind can carry, depending on the speed of the wind, it can be sand size, like a sandstorm, maybe even pebbles if the wind is very severe. Or you think of something like a hurricane, boulder size sediment, like cars can be moved, and therefore probably car size things. But generally, wind is moving smaller sediment than water. Wind generally has less erosional media for a given speed, has less erosional power for a given speed. So usually smaller sediments. And because of that, we get something, especially in deserts, called desert pavement, which is where, let's pretend we have a little landscape here of lots of different sizes of sediment. So I've drawn pebbles, I've drawn sand, here's some silt or clay-sized particles. As the wind comes along, even if it's let's assume it's a very mild wind, what's it going to pick up and blow away?
The top layer.
Well, sure, the top, but which sediment specifically?
The
The smallest ones. And so the wind is going to carry away let's say the clay-sized sediment, which, by the way, dust is what we call clay-sized sediments blown by the wind. And in geology, we call deposits of that loess. It's a German word which kind of just means dust. But the very, very fine sediments blown about by the wind. There's a great example of loess. The trade winds blow dust off of the Sahara Desert down into the Amazon basin. That's one of the reasons the Amazon basin is so fertile, is because this wind picks up loess from all over the Sahara Desert, and the trade winds go like this and just deposit it straight onto South America.
Does that happen in Australia too? Africa?
Possibly, but I don't actually know the answer to that. Like, you mean like this?
Yeah.
Maybe, and maybe more like that. I don't know. I'm aware of this one, this loess current, but I don't know of any others. That's a specific one I do know about. You could be right. So the clay is picked up, maybe silt is picked up, and so what's left behind is just what we call a desert pavement, a pile of kind of almost neatly arranged gravel or pebble or larger sized rock, where what's left behind is just the big sediment, and that's called desert pavement. And what if the sand is blown around? Well, in places where the wind is very strong and there's not a lot of vegetation, what kind of features do you think we might get from sand?
Rock hard. Dunes.
Yeah, dunes. So dunes are like hills made of sand. The direction that the wind blows in general is onto the shallow side. So we call this the windward side. Let's spell that right. Windward side, usually shallower. And then this side here is called the leeward side. You might, and Americans might pronounce it leeward, like the lee side. The lee is the side of something away from the wind. That applies to buildings, it applies to sand dunes, it applies to a sailing ship. The lee side is the side away, out of the wind. So if you take up the wicked habit of smoking, you will probably, I've seen people do this at like Walmart, you develop a knack for finding the leeward side of a building because you can't light their cigarette in the wind. You might have noticed this. You might go to a gas station sometime and there's like a congregation of smokers on one side of the building, especially like in Cheyenne, Wyoming, where there's lots of wind, because they're trying to stay out of the wind. They're on the leeward side of the building. They would make great sailors probably because they know the direction the wind is blowing all the time. Golfers too. One thing that's really interesting about the way that wind moves sediments is that the higher up in the air it goes, remember the processes of rolling and saltation and suspension apply to the wind erosion too, just like they did at the river. But the higher up in the air we get, the slower the wind moves. But also the closer to the ground we get, the slower the wind moves due to friction. And so one thing we end up with is these two kinds of ventifacts. One of them are these kind of mushroom toadstool shaped things, like you might see even at Toadstool Park. Another one is arches. And those exist because the wind can carry the biggest and most sediment here. Here, too close to the ground, so too much friction. Here, too far off the ground, so it has dropped the things that it was carrying. And so we get this narrowing mushroom-shaped toadstool structure, which is sometimes in some places called a yardang.
So that's what happened at Toadstool Park?
At Toadstool Park, it's a little bit different too because the top of the toadstools are a different and more weather-resistant material, but it's the same similar kind of process.
Because the bottom is like...
This is probably siltstone, yeah, or maybe shale, depending on what kind of rock. And then the top part is probably sandstone. This can form, if there's any kind of vertical defect into it, that vertical defect is widened over time and that becomes an arch. And these two things are called, and there are others too, the dunes are also called ventifacts. Ventifacts, like artifacts from the wind. Venti is the Latin word for wind. So the wind artifacts, the ventifacts. Check.
The buttes formed mostly by wind erosion.
So the buttes themselves were formed primarily by water erosion, like just runoff of water. But yeah, well, the places where they were actually, it's really interesting with the buttes, is that imagine the whole land is flat and roughly level with the top of the buttes. That's how it was in like the late, in like the, when the dinosaurs were dying off in the Cretaceous. The places where the rivers were running had limestone channels, and that rock is quite a lot harder. And so then as everything started to flow downhill with the rivers that later came through, the things that had the limestone channels were harder and more resistant to erosion. And so where there are buttes now is where there were rivers when all of this was underground. Kind of interesting. So the mass movements, gravity, let's just draw a little arrow on this one. I'm going to do this in purple, I think. Let's just go in order of speed. If it falls fast without touching any land, it's called a fall, like a rock fall. It might be called an avalanche if it's snow, although that doesn't really count as sediment. So a fall is if it falls without touching anything. And then the next one down is a slide. And that's where it is moving quickly, but it is in contact with the slope the whole time. A slump takes a longer period of time, and then the slowest one is called creep. And it's just when the whole land kind of moves very slowly. So falls are the fastest, creep is the slowest. Falls can move boulder-sized sediment, and creep is generally just moving maybe topsoil or other loose, unconsolidated material. Trying to think if there's any specific other stuff. I think if you have done your self-check, you will be able to use your notes on this test.
Yay!
Oh, the test does talk a little bit about wetlands, and I don't know that your book does, so you might do your own little research on wetlands, and also I will help you during the test. Do you have questions about any of this? I mean, we've talked about most of this stuff in general before, but I just wanted to draw out the specific features that are caused by these things. Yes?
Gravity erosion completely depends on the other ones, right?
We only call it mass movement if it's primarily influenced by gravity. So like a fall can happen whether the ground is wet or dry, whether there's water or not.
But
it's just gravity.
has to be eroded.
Yep, probably. It has to be on a slope. These are usually slope dependent. Just like we said for the river erosion, the gravity itself is not going to change. So what really changes to determine the feature is the slope. Other questions? Thank you, Hunter. Bye.